Okay, let me make sure my mic is on and let me double check on that. Hey everyone. Awesome. I think I'm live. We can get started. So we're the plan for today is to go through G2Net gravitational wave detection, where you're supposed to find gravitational wave signals from black hole collisions. And I quite literally think I started. So I remember the meme of becoming astrophysicist overnight, an expert in that. And I have been watching a lot of physics videos for the like past 2 or 3 days. So I'm honestly excited to be sharing all of that knowledge as well. If you're new to these live streams, what we do here is we try to understand tricks from the top performers on any Kaggle competition. I and hopefully you all believe that there's a lot to be learned from them and that can be applied anywhere. Broadly speaking, so that's the general plan for today. Usually in the first half, I try to share general tricks and how do you go about specific competition, and towards the later half we start going through the top solutions and we start to discover many common themes, and usually there's also fine differences which we learn. So without further ado, let's get started. I'll start with a quick refresher on how you work with spectrograms. So images of waves. And for that, I'm going to use H2O's hydrogen torch again. Because people like Yauhen and absolute Kaggle legends have created it, it always makes for a great tool that I can simply use and explain stuff. So what I want to remind everyone of here is I have a data set on audio classification, and audio waves are somewhat similar to gravitational waves, not really, but they are waves. And the thing we I want to refresh for you all is hey Santosh, thanks for joining. And the thing I want to refresh for everyone is that while working with waves, you create spectrograms and you create CNN models on top of it, and you can pre-process the spectrograms in different ways. So for that, I've loaded this data set up, and let me switch to master so that I have more settings to play around with. I am only going to run this for 1K fold, use the entire data set, and the audio parameters are set to auto. But what I'll do here is I'll switch this to manual. So if you'll see here, you can see that there are different sampling rates that you can play with. You can chunk the training data into a few seconds. You can set the window size, which means how many. It's basically like a sliding window across the signal. And then you can decide how to create frequency bins. And for me, I'm always forgetful of this. So when I look here, it says it defines the number of frequency bins used on the Mel scale spectrogram. So now I remember Mel scale is one of the ways to create spectrograms, and there are different ways on how you can normalize spectrograms as well. So for example, this is audio, but you could do the same for the spectrogram. You could have mix up there. A few of the teams did do this, and then you could decide whether you want to use an ImageNet pre-trained model, yes or not. And the teams mostly used, so the baselines were EfficientNet B7, and then a few transferred to SE ResNext, which also fortunately we have here. ResNet 34 was also pretty popular at that time. And I'd like to use gem pooling here, and you can then play around with different settings if you want to use differential learning rates or stuff like that. Basically, this is how you work with any form of wave data. So I ran this exact experiment earlier, and as you can see, in just about 5 minutes, it gave me an incredible ROC. And the thing I want to remind you all is this is what it ends up looking like inside the memory. So when you actually translate it, Call of Duty, I see Sanyam, I hit like thanks Ayush, thanks for the support. If you enjoy these live streams, please also consider liking like Ayush did or subscribing to the channel if you enjoy the live streams. So coming back to the point, this is what the spectrograms look like inside the memory. And I don't know about you, but I can absolutely tell nothing from this. But apparently, this was a sound wave. And gravitational waves aren't any less complicated than this. uh, this is a way for me to fiddle around and see the best and worst validation insights. And again, as you can see, this would greatly vary with how you pre-process different spectrograms, right, or different waves. So for hydrogen torch, it also makes very easy for me to go through the grad cams, which tells us which part of the image was actually helpful for the models to understand, and which were the best or worst performing models, and then we can adjust our pre-processing accordingly. So when you're working with any form of wave data, you'd ideally like to convert it into a spectrogram or an image of a graph. Why would you do that? The simple reason, as I found through the forums, was even though you have models that can directly work with time series stuff or audio stuff, image models have been progressing so much more that using this path is better than that. When you do that, you can pre-process with different ways, and then you create a CNN model and go about figuring out how that learns these fine features. So this was a quick refresher on how we work with any form of waves. I see Ayushman in the chat. Hey Ayushman, and shout out to his team. I think they finished fourth in this competition. So we have another legend in the chat today, and I think he's competing in the next RSNA as well. So he might get a solo gold soon. Shout out to Ayushman. We're doing shout outs now on this channel. um, okay, so it's quite similar for gravitational waves, and what I'm going to do now is I'm going to condense the info I've gained from these two absolutely awesome channels. Physics Girl is a channel by Diane, and she makes it absolutely awesome to understand very complicated stuff in very easy fashion. And Veritasium is also one of the popular channels. I watched a lot of the videos here, and that helped me understand how you actually work with gravitational data. So if you can indulge me for a second and assume this handkerchief is space and time. So this is reality. It's quite literally the fabric of reality right now. And if you have any mass in here, the mass tends to distort space and reality like so. So let's say there's a mass in the center of this. It would distort this. Sorry for the bad visualization, but it would distort this continuum by creating gravitational waves. So around this area, there would be a gravity pulling towards the object that exists there. That's simply put gravitational waves. And when you have black holes or neutron stars, which are simply dying stars or dead stars, quite simplified, they tend to create a gravitational wave around them, which you can think of throwing like a stone in a puddle, and that sends out these gravitational waves into the universe. When you have two such black holes, they might be rotating around each other. So let's say this one is going in this direction, this one is going in this direction. They would emit these waves, and since the energy is preserved, they would slowly and slowly spiral into each other. So instead of going in perfect circles, over millions of years, they would actually come close and collapse into each other. So these two black holes would actually become one simple or one single entity. And when this happens, there's a large amount of energy sent out to the universe, quite literally. And that's what we're working with here. The centers mentioned here, LIGO, and there are two LIGO centers that are capable of measuring such sensitive waves, and that's what they're trying to record. So how do you record these waves? There's a simple way of doing that, and again, I learned this through the two channels I mentioned. But what they do is they have an incredibly long tunnel, and they have another perpendicularly incredibly long tunnel. So they send a laser wave at the same time through both of these, and then the laser bounces off a mirror at the end of these tunnels. and it returns to the original source. Let's say this is the source, these are the two waves, and it travels and returns to this. So these are very distant and very long tunnels. And if a gravitational wave happens to pass through this, let's say, this arm, in that second, the wave would be ever so slightly distorted, because gravity distorts space and time. The wave would take nano, micro, whatever small scale seconds more, and its wavelength would slightly be out of phase with the other wave that's just gone out. So let's say ideally both waves would return like so. Maybe if there's a gravitational wave experience, the other wave is slightly so shifted and it returns like so. So this is the kind of data we're working with, and these wave signals is what is actually present inside of the data. So we have three different centers for that. And why is that the case? Let me switch to Pendada's incredible notebook, and I'll remember to upload that. So what I'm searching for here is there's a map that shows where these centers exist. So here's the two centers, and here's the third one. These instruments, that tunnel that I mentioned that measures these gravitational waves, are incredibly sensitive. So they could easily be affected by any external noise. And these actually, I watched a lot of documentaries, so maybe I'm nerding out a bit. But like these are created in absolutely isolated areas. So like they're out in the forest, so that even a truck driving near couldn't affect the distortions. And they tend to do that. So vehicles can even distort these measurements. For that reason, these labs and these like LIGO centers are very isolated. Even then, you could have distortions that could give a false positive. So for that reason, you have these three centers spread across the world, and two of these exist in the United States at very distant places. So if the wave is detected in one of these labs, and the same wave is also detected in the other two, that means that yes, that was a true positive, and you can then start to work with that signal. So we have three such labs as data to work with. Hey Pooja, thanks for joining. So now, as I mentioned, you have three such labs, and you have simulated data here. So as you can imagine, gravitational waves are extremely rare. The first ever recorded incidence was very recent, and that was two black holes that collided 1.3 billion years ago. So it's all of these occurrences are extremely rare, and most of the data here would be simulated because it's otherwise you'd have like an insanely imbalanced data set. So the signal inside of this data is simulated, and the hosts claim that the noise is real. So whatever noise is present inside of the data set is actually true noise. um, the reason why again we going through this competition is because there's a new G2Net competition which is quite similar to this in many ways. So there's still 3 weeks to take part in that, and you can hopefully apply all of these ideas from here. um, a few more key details wherever we refer to in this live stream from here on out. GW means gravitational waves. um, I could switch to the data tab and mention that very briefly once that loads up. So this was an insanely large data set. As you can see, it's about 70 gigs, which means there's a lot of pre-processing techniques you could have applied. Um, and the files inside of here are simply NumPy files, because this is just the wave data, and then you have to process and convert this into an image that most of the teams ended up working with. So to my knowledge, no team has directly worked with this data for this competition. Let's quickly read through this. The training set is time series data containing simulated gravitational wave measurements from three wave interferometers. There are the two LIGO ones, and there's one in Europe which is called Virgo. Each time series contains either detector noise or detector noise plus a wave, and the task is to identify when a signal is present. The parameters that determine the exact form of a black hole waveform are the masses, sky location, distance, and a lot more things, right? These parameters have been randomized and used to generate these signals in the data. So it's very realistic, very realistically generated simulation, and each of the data samples has three time series, all of which span 2 seconds at the sampling rate 2048 hertz. So remember, while we were working with hydrogen torch, you could decide the sampler rate. So if I was working with this data, which I wanted to upload, but it's such a big data that I actually ran out of disk space. So that's why I use another example there. Side note. But the sampling rate there would be 2048 hertz. So now let's go through some EDA kernels to understand a bit more about the data set. This was a kernel by Yaroslav, and he showed how to work with EfficientNet B7 for this dataset. So the target is very well balanced. It's a 50-50 balance. So 0 is when there's no gravitational wave being detected, and 1 in the target represents when there is indeed a gravitational wave. Throughout this kernel, he's plotted these signals separately and then all together. So if you look at all of these waveforms, right, individually they make somewhat sense, but when you plot them together, you can also see that they're quite different from each other. And the another thing worth remembering here, when a gravitational phenomenon is observed in these waves, it's not at the same time for all three detectors. So the black wave could have a spike at somewhere else, the green wave could have it detected somewhere else, and the red could have it detected somewhere else, just because these labs are spaced out and it would take some time for the wave to travel from one detector to the other. So you wouldn't see a same spike everywhere, otherwise this problem would be too easy. And it's a Kaggle competition, so it's meant to be hard. um After this, he in this kernel teaches you how to create spectrograms and walks you through a few transformations you could apply. There are a lot of transformations that the team would be working with. So I'll only mention a few. There's Q transform, which will be really popular. So some people will refer to CQT 1992 V2. This is the exact algorithm that exists inside NN audio. But this is Q transform. This is also CQT. This is also this exact thing. The thing you would end up working with here is you would probably fiddle around a lot with the hyperparameters. The sampling rate would remain the same. Many teams apply data augmentation in different formats, and we'll also learn about that. There were other transforms as well that people had applied. There's also a time series component, as I mentioned. So some teams also applied a LSTM layer on top of their CNN models. I think that's all I wanted to highlight from this kernel. So I'll move on to the next one. This is by Heads or Tails, who's one of the absolute legends in the community and always writes these incredible reports. So I'll probably also use some insights from here. Um, the evaluation metric here is also ROC Uh, and he also highlights that the simulated part, the waves are simulated, but the noise is always real. So from here, he showcases how the labels exist, and the target is either 1 or 0. For the test data, You would have to submit submissions like so. So you will have an ID along with the target. The sample submission shows what our prediction should look like, a probability for the signal being present. The training folders exist like so. So you have the ID, and inside of the training folder, you have folders existing like so, where the paths, where the exact file exists. And the last occurrence inside the folders is the ID or the file name. So the file name is the ID, is what I'm trying to point out. There were no missing values here. And there was a quick mention that this indeed has a time series component to it. So here he also points out that the sponsors weren't kidding when they wrote that in nearly all cases, these signals are not visible to the eye. So at least I was thinking that I could probably look at all of these graphs and maybe make sense out of it. But the thing I understood is that these three sensors, if I may, work. I'm calling them sensors, they're much more than that, but these three sensors have different sensitivity. So a spike here wouldn't be the same spike in the other ones. And there would also be a time series component. And even if you can see spikes yourself, they usually may not mean what you think they mean. So if you see this spike inside 3, it's not necessarily a gravitational wave. And that might not be true for all examples. So in the previous one, it actually was. But in this case, the target is 0 and we still see a spike. So you might be tempted to think that, hey, this is a gravitational wave. I can see it in the graph. That's not true. That's just not true. Um, that's another added challenge to this competition. I think that's all I wanted to highlight in this kernel. I'll use one more kernel from Laura Fink, who's now a part of the H2O team. So she's joined the H2O team and she's also bringing her amazing insights to the team. And I was really happy to find out she joined us recently. I think it's been a few weeks. But anyways, you'll see that her kernels are really high quality. Um, and as she mentions here, it's basically like looking for a needle in a haystack, since the data contains not only the signal but there's also some noise alongside the signal for whenever a signal is present. The reason I wanted to use this kernel is because she's actually shown how you pre-process the waves and how that actually looks like in the graphs. So I'm not going to point out the individual names of the algorithms, but I just want to showcase what it actually looks like when you process these. So the first one she mentions is whitening using the amplitude spectral density to eliminate the noise in the AST range, low and high frequencies, as well as close to the spectral lines. So this is one of the pre-processing ways, and the other one is band pass filter. So whenever you're applying a filter to any wave, you're basically filtering out either high frequency waves or the lower frequency ones. So you could think of it like let me draw up a terrible visualization again. Oops, sorry. So let's say this is a wave, and you create, let's say, a filter that filters out the lower end of the frequency. So you would have this clipping function. This is a simplified representation. You could have complicated ones as well. But basically, everything under this would vanish after that. So you just have the part of the waves above this then. So this part remains after you apply this particular filter, if that made sense. So here are a few visual examples. Here's a simple sine wave, and then she goes on to elaborate what is a low frequency wave. So the sine wave in this case becomes a low frequency wave because, as you can see, it only phases twice. But the other blue wave is a high frequency wave because it completes itself many times. So whenever you're applying a transform, you're changing the wave in some ways. So for example, you're converting the high frequency wave into sine like wave in this case. And similarly, you could apply a lot of transforms, as you can see in this graph. You could also have sliding windows here to work with the data. And then you could also have filters that work with this. You could also have windows that you apply to these that change the characteristics like so. So you change the amplitude whenever you apply um, a window. And amplitude basically, for sound, it means how loud the wave is. Or you could think how much energy is being transmitted there. So as you can see, this is the original data here. One window is applied to it, which changes it a bit. So you could have Tukey window applied, which changes the characteristic a little bit differently. But the thing I wanted to point out here is you have these different transforms, and we'll hear these names throughout the top solutions. You can't, I couldn't, maybe you can. I couldn't tell what they meant visually, but apparently a few of these, when applied with a bunch of settings, actually help the model learn some fine nuances, or those are helpful before creating the spectrograms. Or you could also apply those to the spectrograms. So you could apply image augmentations to the spectrograms. Visually, when you're looking at the waves, they might not make a lot of sense because again, this is like very sensitive wave data that you're working with. There's also whitening, which I think only one team could effectively work with. So, in this section, Laura mentions that the data is dominated by low frequency noise. You could divide the Fourier coefficients by an estimate of the amplitude. And remember that, at least for me, I have studied electrical engineering, but I basically worked my way around just passing the exams. What you need to understand from these write ups is whenever someone says Fourier transform, it's a function that you call, and you divide it by something to make a transformation, stuff like that. If you're curious, you can learn about it a bit more, but for me, if I was taking part, I would just apply that and see how that changes my leaderboard position. So FFT is Fourier transform that's being applied here in this function if you pay attention. So this way we perform a down weighting of the frequency where the noise is loud. And then to return to the time domain, you apply another transform. So whenever you're working with different transforms, again, it's just to filter out the signal and try to find out the signal. Let me close the irrelevant ones now. I think I had a few things to highlight from this kernel, but most of them have been covered already. So I'll skip this one as well. Um, there's a post by Fractal Feelings, and I'm a fan of their username. They're sharing things I've tried and how they worked out. This was the first time they were trying out a neural network, and as you can see, they finished in top 10. So if you work hard and if you're incredibly smart like Fractal Feelings, you could also get a gold in your first competition. He says he tried a lot of things, and here's the learnings. For his model, he had applied a bandpass filter and rescaled the wave form, applied a time frequency transform. So whenever you see CQT, think of that function I had shown, 1992 CQT. It's a Q transform. And then CWT is a wavelet transform. So where did everyone find about all of this? Someone created a kernel that they ended up sharing, and hopefully they watched a few videos or they read a bunch of papers that led them to it. So in this case, Anjum, his Kaggle name is Datasaurus. His real name is Anjum. Shared this kernel on how you can create a continuous wavelet transform in PyTorch and how can you do that really fast. And then it also shown the visualizations which didn't make any sense to me, but I assume this helps with some form of pre-processing. So that was my understanding here. So all of these transforms are applied to create a scalogram, and then you classify using efficient net. So this is simply a binary classification problem, right? Once you apply all the pre-processing and whatnot, at the end of it, you will have two images with the label 0 or 1, and your CNN or your attention-based model is just supposed to classify between those two. So that's the goal of this competition. So the things worth highlighting here is what he learned from experimenting. The bandpass filter has quite an impact, and this is because the noise below 20 hertz is quite high, and the signal is weaker at low frequencies. He chose 500 hertz because the highest signal frequency for a black hole event is at 350 hertz. He could not find articles on the frequency range, so 500 was a safe bet. Rescaling was essential. He started with constant quality transform and found this is a lot faster than Librosa. So Librosa is a library for working with audio data. So it's an open source package for music and audio analysis. And as I started this presentation, this can be really similar to audio processing, right? So Librosa becomes a default library you might work with. Many people use NN audio because again, the waves are quite similar. Hey, machine learning. Thanks for joining. I laugh because that's your username and I'm calling you machine learning. Um, he discovered a TF implementation on CWT and updated it to 2.0. This gave him a single Keras model for scalogram that runs on TPU. Larger, all of this allowed him to work with larger image sizes. So the scalograms could be 256 by 256 or 512 by 512. Different wavelength width. If you are working on the new competition, these would be parameters you fiddle with. If you are just watching this for a review or refresher, these are parameters you work with. And when you actually end up doing that, you might want to pay attention. For me, this makes sense in like it's an experimental documentation. And if I ever come back to such a problem, I'll probably watch this video or just reread this. That's why I'm not like highlighting individual things. Hey, what's a wavelength width, and why does this seem optimal? It's all experimental, I would assume. So for transfer learning, he says that he had frozen a few layers and then unfrozen. This gave him marginal improvements, and different efficient models gave him slight boosts. These were the broad learnings, and I'm slowly moving my way towards the final solutions. So these were the learnings by fractal feelings. For everyone else, while they were starting out, Nakama always shares absolutely high quality starter kernels, and he had shared these kernels that you could simply use and basically work with B0, and I think he later updated it to B7 models. So these were giving you a CV at that time of 0.819, and the LB score was 830. And then later he also taught you how to apply the Q transform approach, which gave a nicer boost, as you can see. So the final scores in the LB were around 0.88. So as you can see, people really improved on top of this, which is what we learn and how they actually did that. And again, the thing, if you pay attention, is there's a nice difference between the first two teams, right? Relatively speaking. And whenever this happens, usually there's some magic happening. So the leaderboard can also tell you a lot of stories. And this would mean that they've found some magic feature or some magic approach. And that was actually true. So they had somewhat reverse engineered the way in which the data was simulated. Somewhat, not completely. Otherwise, it would be a perfect score. So K Killer shares some advice on working with wave competitions, and this is where I learned. I mentioned this earlier, but this is where my knowledge came from. So thanks K Killer for that. Moving wave data to images leads to better performance. You might be tempted to go the other way, but the fact is, advances in image processing are such that transforming the wave would always give better results. And then he says how you could perform these transforms. There are many different ways. And usually you'd want to feed them to an efficient model or some model from the ResNet family. Remember that spectrograms are not like other images, and essentially, because they include time dimension, you can use an SED model or a well designed pooling strategy. And in the comments, he had clarified that SED refers to sound event detection models. So after you've applied all of these transforms, you might end up with an image that looks like this. And if all is working well, your model should be detecting the signals like so. So this is a true positive example that Heng has posted. And this is true for all three detectors. So he's shown us the examples for all three detectors here. And then there's also a false positive example. Again, visually, the challenge here was you couldn't tell anything from the data. So that's why it's somewhat of a harder problem still, because as you keep doing this, you just have to rely on the scores and CV when you're working with this. Yasin had shared this post about CQT, and then I actually read through this and learned that there's a lot of theory here. Thankfully, it also shared an implementation of it. And as I mentioned, this is the CQT that most of the teams ended up working with. So simply create a run CQT transform function to which you pass a NumPy array. And on that, I believe you call this particular function CQT 1919 v2. There was a lot of discussion around whitening as well. So I believe only the third place team made it work. His interpretation, Anjum writes, his interpretation of the whitening is to normalize the amplitude of different frequencies. So it's like turning the volume down. And on known sources of noise of a certain frequency, which can drown out the signal. So he plotted all of these different waves. He shares a plot of them that showcase the noise. So for unknown sources, for example, if you have AC current or disturbance from vehicles going along the road outside the lab, you could have notch and bandpass filters remove those noises. But when the data is simulated to look like LEGO, it is not exactly the same. So you cannot design the actual design curves. But then he showcases how you can derive those design curves for all three detectors. Then he showcases how to apply the whitening. He claims that all of the sources of the noise can be found to spike around 306 hertz. Not a lot of post processing is needed. In fact, his models didn't need any bandpass or notch filters after this. So, just whitening would dampen out a lot of low frequency noise for his case, and the gravitational wave would emerge out of this noise on a Q transform or a wavelet transform and also help his 1D models. So, what's essentially going on here is, and we'll quickly reach to the top solutions, but just as a refresher on what we've been reading about, you have these, sorry about that, NumPy files, right, which contain the wave data. And this is sampled at 2048 hertz. It's 2 seconds long. It's from three different labs. You take this and then you apply a bunch of filters. So this is still the wave data. You could have something that removes high frequency. You could have something that removes noise. You could focus only on a few frequencies. The way you do that is by removing everything else. Um, you could also apply a bunch of other transformations. Once you've done that, these could also include Q transforms and wavelet transform. So you could have CQT and you could have CWT. After you've done that, you create a spectrogram. So I'll change colors again. This is my way of being artistic, everyone. This is my peak art. Uh, so you have a spectrogram somewhat at the end of it. And after you have that, you could simply apply a CNN model. So this could be an efficient B7 model working with the target 0 or 1. And then you could have the probability from its logits telling you if there's a gravitational wave inside of it or not. All of the transforms, CQT, CWT, the filters are basically to get this in a format where it's easy for this part of the problem to detect waves or to detect signals. Visually, if you actually try to understand that, it might not make any sense at all. So, the best way to do that is by adjusting the parameters. And here's a discussion by Heng again, where he says he's created this plot of LB score. So if you have a larger image or a deeper model, it could lead to a better LB score. So he shares different hyperparameters that were helping him and how that affected his CV and LB score here. He also found a interactive web app where you could actually experiment and see. So the main side quest when creating these models then became, how do you optimize this? How do you optimize these knobs of all of these pre-processing methods? And he had also summarized different approaches here after reading a bunch of papers. One way basically to find the optimal parameters would be reading a lot of papers in the domain. The other could be just experimenting. I assume many people did both of that, and that's how they came up with all of these. So here he shares the configuration and then how the folds perform for B0 model, efficient V2 small, so on and so forth, and how the ensemble performs. Uh, I think we get into the solutions after this, but one more thing to highlight. Yasin shares things that he learned in no order. Make your baseline run as fast as possible. So, since it's an 80 gig data set, right? And since you're doing a lot of pre processing, it's best to figure out what's the optimal way to store these spectrograms, or what's the optimal way to apply these pre processing, or any part of the baseline that you run multiple times should be as fast as possible. So, you should spend some time optimizing your baseline so that you can have the fastest results there. Don't underestimate possible solutions. So for his case, he had focused on 2D models and put 1D models aside. Many top teams actually use 1D models, so it was a regret for him. He says you should use public notebooks or kernels and include those. So here he also pointed out that you should work with libraries that you necessarily might not with. Um, this competition was easier to work with Keras since the files could be saved in TF record, and that was faster to work with. The last point was join a competition earlier because these experiments take some time to run. I think that's all the in background info I wanted to give about this competition. So catching up on the comments, I don't see anything. So I'll continue with the top solutions. My goal is to cover at least the top 10 solutions here. As a reminder, I won't again go into depth or try to understand why someone used a Q transform or why that worked well, because I don't understand that. And from my perspective, it's just a transformation. It's like normalizing your images that for this particular data set worked really well. And if you're competing on the new G2Net, it might be worth trying the exact same hyperparameters. So I think three or four of the top teams have made their code open source, and you can simply build on top of that. So the top team, as I mentioned, actually found out how the data was being simulated, or they created an approach where they could simulate or add more data. And there's a link to a kernel here that actually shows that, or there's a link to the GitHub repo that actually shows that. So in this write-up, they say the problem was that the neural network couldn't even start to learn without the filtering. So they played around with a lot of filters, and he says that they chose a double application of FILT, which is a filter of fifth order high pass filters at this particular frequency. Experiments showed that they can freely decrease the order down to 2 and critical frequency down to 15 hertz. The next step for them was to converse the data processing to whitening, and their team just decided to skip it. In the 1D approaches, neural networks should derive filters from the data, and they had no tangible way to preload a calculated filter. As soon as they found out that the noise was generated, they proceeded to generate their own noise, and this was helpful since they were already overfitting a bit. They say the signal was probably generated on higher frequency with idealized PSD. So they checked, and just generation with observed PSD was good enough. There were some added noise that they also, I assume, added to their particular data set, and these end up in an additional notch filter. Then they thought, hey, if we're able to design the noise, might as well design the signal, right? So that's what they explain from here on out. And again, it's very specific terms about different approaches. So I think it's worth going through these when you're reading it. For me, there's no individual trick that stands out, so I'll skip that. As a reminder, you can also simply run their code from here. In this discussion, Grandmaster Jiba had shared his approach at an attempt to replicate the generator. So the deep learning part is where the things get a bit more interesting, and this is also from the top team. So they had all of this data, and it was of course being fed somewhere. Uh, Here's the visualization of their model architecture. So these are the name of the three labs. This is not an approach. And then FILT, as I mentioned earlier, was just a filter that was being applied. So all of this data is fed into three con 1D encoders that then is led into a ResNet 34 backbone. From there, you can get the probability. You can get I assume they mean they applied a Q filter to this or a SNR layer on top of this. Let's read this to just make sure I understood it correctly. So they say they tried different approaches. The CQT could not improve their score past 0.87, and the top score was 0.88 if you remember. Spectrograms with NN audio was a bit better, and working directly with raw signal was much better. And they discovered that applying a high pass filter on a 1D conf on stacked channels quickly produced good scores. So it was much easier to work with this. And the model was just a bunch of simple convolution followed by batch normalization followed by SILU blocks followed by max pools. And he also shared the kernel sizes for the blocks. They'd used channel shuffle for two of the labs and minor time shifts between the channels. This approach got them to 877 score. Since the model was already overfitting, they switched to SGD with weight decay and this particular approach from momentum. This gave them a further boost. So tweaking the hyperparameters improved their score a bit further. Then they talk about how they improved the con 1D model. So since the synthetic data they were trying to work with wasn't good enough, they tried maybe optimizing the 1D model could be a good approach. And from there, they followed the Inception V3 like architecture and created kernel sizes like so. This gave them a nicer boost and got them to the score 0.883. Here they shared the main building block for the Con 1D model. So it's a bunch of silu blocks with different kernel sizes that have been highlighted here and in the write up. All of this is then concatenated and finally fed through a linear layer, if I understand correctly. They share the hyperparameters here and the augmentations again. So frequency masking, time masking, small shifts, and channel shuffles were used here. Finally, they shared that synthetic data gave them a further boost. And they shared how they ended up with this score. They also, in the model, so I'm trying to debunk this myth. They also predicted signal parameters during pre training. So these were predicted that by the model and not applied after this. Sorry, I misunderstood that part. So this is not being applied to the model, but it was actually being predicted by it. I'm skipping a lot of things because I only want to highlight the tricks here as a reminder. So I don't intend to always cover everything. So things that did not work for them, they tried denoising autoencoder. You know, a solution is very cool when you actually read a part of it and you think, oh, maybe I should have thought of that idea. So when I was reading this, I thought that sounds really cool. And I don't think I would have come up with that idea when I was working with the data. Actually, when I interviewed Mark Landry, he said this that you are working with absolute legends, and many a times you look at their solutions and realize in the same time frame they came up with something much cooler. That's what makes Kaggle so cool, right? I'm trying to find Mark's profile, and Mark Landry he said the exact Exact same thing when I was interviewing him on the series. So denoising an autoencoder did not work for this team, and OHEM collapse and reverse labels also did not work for him. So here he describes the experiment, and I'll skip over that. Um, because the main trick for them was to working with the synthetic data and then creating this 1D model that was being fed on top of it. So one thing I learned here was they used a Silu block, which I don't think any of the other teams have. So that was cool to see. After this, we'll dive into the second position solution. I'll remember to upload it. This is also open source. So this was a solo goal for uh, I don't want to butcher their name, so I won't say it. He shares the common settings for all of the functions, and for him, it was a five-fold CV. He had used a cosine warm-up scheduler with a BCE loss. He shares that there were different architectures that he played with. Um, Trainable front end outperformed fixed front end. So when he says trainable front end, it could be a 1D CNN model. So it could be a ResNet 1D18 test DenseNet 1D 121 or a simplified WaveNet. It could be a WaveNet wavegram. These are just architectures. If you look these up, you can find them and actually go through them. That's why I'm skipping over them. And this was another one that he came up with. So you could have the waveform that's fed into a convolution, which then goes through these three different layers separately and it's stacked together. You could also have a fixed front end where you just pass in the continuous wavelet transform. So for him, he said the trainable outperformed the fixed ones. He applied a bandpass filters to all the networks, and for his case, whitening did not work. For augmentation, there were several types of augmentation on wave and spectrograms, and only a few of the wave augmentations worked for him. So he added Gaussian noise to 2D CNNs and flip wave amplitude for 1D CNN. Pseudo labeling improved his score uh, ever slightly so, sorry, and label smoothing also helped a bit. Also shared that stacking was helpful, so he created a ridge regression model to combine all of these outputs, and this gave him a consistent boost. After this, he shares the scores of individual models, which I'll skip, and you're welcome to read through this. So he shares the front end, which then feeds into the back end and the input sizes. So the best performing models were on 1024 by 128, and yep, all three are on that particular size. Hey, Umang, thanks for joining. I'm just catching up on the chat, and I don't see any questions. So maybe everyone else is new to these transforms, just like I am. So for the third place solution, the models used in their submission was a 15 1D models and 8 2D models. This competition, and the same is true for the current G2Net, don't have any kernel restrictions. That's because the data is so damn huge, you probably might not be able to run inference under 9 hours. Um, for the 1D model, there was a customized architecture at wave detection, targeted at wave detection, and the following test time augmentations were applied. So a vertical flip, which is really interesting, right? For waves, you might not imagine vertical flip might help. For this case, it did. Uh, Shuffling channels for one particular signal, adding Gaussian noise, applying time shift, time mask, and dropout. So for his case, he had also pre-trained with the waves and then used training with pseudo label or soft labels. He'd used rank loss and applied mix up as well. Also shares the pre-processing tricks that he had applied. And for him, he did apply whitening with Tukey window. And he had also applied simulation. So he'd also tried to create uh, simulation of the data. That was the TLDR. He also shares how the 2D models were created. They created the 2D models using CQT and CWT images with whitened signal as input. They also tried various augmentations for the 2D images, but most did not work here. However, mix-up did help counteract overfitting. After that, he scores different models and approaches that were helpful. I can skip over that. And here's an overview of their approach. So you had these three different labs from which you would have an extractor that would basically collect the signal or collect features from the signal. These were passed through different res blocks, and the same was repeated a few times to match the signal from different detectors. After which the signal was actually detected by passing it through res blocks, and we see the CLU layer here again. So I assume this might have originated from a Kaggle kernel where someone used it and everyone built on top of it. Here they mention that CLU gives improvement instead of ReLU, and gem polling also was helpful. They share a few hyperparameters and the scores. For things that did not work, larger models and use of smaller or larger con sizes, attention blocks before pooling or res blocks, densely connected uh, layers were also not helpful. They also share the pre-processing tricks that was helpful for them. So I'll only go through the TLDR. For 1D models, extending the signal was helpful. Applying a Tukey window with this hyperparameter was helpful. And whitening with values based on average Fourier transform of all negative training examples. For 2D transforms as well, whitening the data in CQT transform. And then they share the hyperparameters that was helpful for this. So they had also worked with simulating the data, and then they share how they applied this approach. They had also applied adversarial validation to make sure that train and test data do not have any hidden differences in them. After this, they share how they went about applying the ensemble together. So this was for one of their submissions. For the second submission, they share their approach for creating the OOF predictions and working with that. I'm only highlighting these at a very high level because, again, all of these filters for me only make sense if you're actually working with the model at that time. So if you are working on the G2Net ongoing competition, come back to this and actually use these layers. I'm only glancing at the tricks and not going into depth for that reason. So this now is the fourth place solution. And for them, I think it's easier to go to a LinkedIn post that was shared somewhere here. So let me quickly find that. Um, Found it. So Rajneesh had shared this approach, and also quickly want to mention Rajneesh. You should definitely find him on Twitter. He's working on his startup that creates synthetic data, and he's also competition master, one of the highest ranked competition masters. Um, this was the fourth place's solution overview, or this is rather just their architecture. So you had the wave, that was fed through a pre-processing layer. Both the left and right parts work with the same data, but let's only focus on this one. So you had the Tukey window and band pass filtering being applied here. After that, some augmentation was applied, which include time shift and colored noise. From here, parallel conv blocks are applied and then they were concatenated together. So when I see concat, I think torch.cat. After this, they were passed through a 1D CNN architecture where they were passed through batch normalization, ReLU, and con 1D layers. And different downsampling res blocks were used. At the end of this, a LSTM layer was applied, and this was concatenated while also using a skip layer here. The secondary approach to the ensemble was applying similar pre-processing layers and similar augmentation, but the only difference here was a 2D CNN architecture was used. So for 2D CNN, as we've learned from all the solutions, you need some form of pre-processing. So CQT transform was applied, and they also share the hyperparameters here. From there, different efficient nets were trained, and the outputs of both these models were then ensembled together. Let's see if there's anything else in the write-up that might be worth highlighting. They mention about their 1D CNN model, which they claim by itself this single model could have gotten them a gold medal. So they say that they had also worked with a mix of LSTMs, GRUs, but could not find a way to beat the normal Con 1D approach that they had come up with. And then they mention a few details of the 2D model. I think that's all I wanted to highlight from this. So we can move on to the fifth place solution from now. This is also a brief write-up, so it's only a TLDR, and there's also a TLDR in that. PSD widening was applied for pre-computed mean of PSD for each channel, and a custom window function that they had come up with, mirrored sigmoid, was used in their solution. They share the augmentations for the 1D model and the settings for the 2D CQT. They also share the ensemble setup for the 2D model. So it was 5 2D CNN models. And for his case, efficient nets were not very good. I think that's the very small details I wanted to highlight from this solution. We're out of time, so I'm considering covering a few more. But I think the solutions after this get even smaller and smaller in content. So I'll try to summarize what we've learned today. Uh, in case you're working with the current G2Net competition, you have these waves from different labs. Now, there are two routes you could take. You could have a 1D CNN model, or you could have a 2D CNN model. For the 2D CNN model, you need to pre-process the spectrograms with different wave filters, different bandpass filters, and you, from what I understood, have to apply more effort towards tuning all that. For the 2D CNN models, all of that is required. But for the 1D CNN, you could simply feed in the waves with lesser pre-processing, and that will give you a better score. So this particular thing was discovered, I think, towards the last few weeks of the competition, and at least the top teams, as you can see, converged on using this 1D CNN. So on top of that, some teams added a LSTM layer, which also helped with the time series component, because if you remember, there was also a time series component. So most of the top teams converged on this form of an approach. I think there's also worth mentioning the eighth place team had shared an augmentation. So Onodera calls it zebra mix-up, and this is how you basically create that. So you sample at the intervals of 4 is what this function tells you. And you could also do a negative flip, which he says only work for negative samples. You could swap with other negatives like so, or you could completely swap legos with each other. So both the data sets could be swapped, both the waves could be swapped with each other. um CPMP also shares some more details here, but I think they can be simply read through that. So since we're out of time, I'll wrap up here. This was again a very domain heavy competition. So if you're working on the G2Net, well, good luck to you. The data is also quite large this time as well. But I would spend time looking at these different filters and try to work with that. I'm sure there's a lot of interesting kernel shared there as well. So I'd probably look there. But thanks for joining. Next week, we'll go through the RSNA's trajectory. So the currently ongoing RSNA competition, I'll try to find something similar to that and share insights from that. We also have a study group going on for the deep learning book. So that's happening every Saturday. If you're curious to join that, it's open to everyone. Once again, thanks for joining, and I'll see you all next week.